Welcome back to our physics class. Good energy is contagious. In our previous lesson, we have learned why things move the way they do according to Newton's laws of motion, law of inertia, law of acceleration, law of interaction. This week, we will study about a physical quantity that can also help us understand better the state of motion of objects at rest or in motion. Our learning target is I can identify and explain the factors that affect potential and kinetic energy. Let's define first energy and work. Energy is a quantity that can be converted from one to another but cannot be created or destroyed. Energy is the ability to do work. In physics, work is done by a constant force acting in the same direction as the displacement of the object. This object gains energy from one that applies that constant force. In this chapter, we will focus on mechanical energy, the energy that is possessed by an object due to its motion or due to its position. This form of energy is classified into two: potential energy and kinetic energy. Potential energy has many forms, like chemical potential energy, elastic potential energy, and gravitational potential energy, which we will discuss this week. On the other hand, kinetic energy has many forms, like vibrational, rotational, and translational. This lesson will focus on translational kinetic energy, which we will simply refer to as kinetic energy. Before we define potential and kinetic energy, let's examine some pictures of objects at rest or in motion. Given the same mass, which among the pots in the picture below will have more damage when they fall and make an impact with a level ground? Why? Given the same height, which among the pots in the picture below will have more damage when they fall and make an impact with the level ground? Why? Pots placed at locations above the ground possess a form of energy called potential energy. Potential energy, or PE, is the stored energy that a body possesses. It is a type of energy that is associated with the position of the body. One form of potential energy that we will discuss in this lesson is the gravitational potential energy, or GPE. Gravitational potential energy depends on its location or elevation from a certain point and its mass. Gravitational potential energy, in symbols GPE, is equal to m times g times h, where m is equal to mass, h is equal to height, and g is equal to the magnitude of acceleration due to gravity, which is 9.8 meters per second squared. Its SI unit, joule. 1 joule is equal to Newton meter, which is also equal to 1 kilogram meter per second squared times m. Take note, 1 Newton is equal to 1 kilogram meter per second squared. The formula to find GPE tells us that it is directly proportional to the mass of the body and its height from the ground. When these pots with the same mass fall to the ground, The one from the higher elevation will have more impact with the ground. Thus, it will have more damage than the other pots. Given the same mass, the higher an object from the ground, the bigger is its potential energy. When an object's height from the ground is increased, its potential energy is also increased. When these pots with the same height from the ground fall to the ground, the one with the bigger mass will have more impact with the ground. Thus, it will have more damage than the other pots. Given the same height, the bigger the mass of an object from the ground, the bigger is its potential energy. Let's apply the gravitational potential energy formula in determining the potential energy of a diver. Determine the potential energy of a 50-kilogram diver when he goes up to a platform with a height of 2 meters, 7.5 meters, and 10 meters from the surface of the water. Let's find the gravitational potential energy. Gravitational potential energy is equal to mass times gravity times height. The given is the mass is 50 kilograms. G, or the gravity, is 9.8 meters per second squared. And the height is at 5 meters. Now, using the formula GPE equals mg times h, then we have 50 kilogram, which is the mass, times 9.8 meters per second squared, which is the gravity, and 5 meters, which is the height. So we get 2,450 joules. For the second height, which is 7.5, we have 50 kilograms times 9.8 meters per second squared times 7.5 meters. Then we get 3,675 joules. For the third height, which is equal to 10 meters, we have 50 kilogram times 9.8 meters per second times 10 meters. Then we get 4,900 joules. According to the table, the potential energy of the diver increases as the height of the diving platform he stands on increases. What happens to the potential energy of the diver while falling? Based on the different positions, what happens to his energy? At position A, potential energy is maximum, while zero kinetic energy. At position B, potential energy decreases, while kinetic energy increases. At position C, potential energy decreases, while kinetic energy increases. At position D, potential energy is minimum, while kinetic energy is maximum. While falling, the height of the diver from the surface of the water is decreasing, which decreases his potential energy. His potential energy is converted into another form of energy possessed by moving objects, which increases while he is falling with increasing velocity. This energy is called kinetic energy. Kinetic energy is the energy due to the movement of a body from one point to another. It depends on the velocity and mass of the body. Kinetic comes from the Greek word kinetikos, which means moving. Translational kinetic energy is equal to 1/2 times mv squared, where m is equal to mass and v is equal to velocity. The SI unit is joule. 1 joule is equal to 1 newton times meter, which is equal to 1 kilogram times meter squared per second squared, which is also equal to kilogram times meters per second squared times meter. Take note, 1 Newton is equal to 1 kilogram meter per second squared. There is a direct relationship between kinetic energy and mass, and also between kinetic energy and the square of the body's velocity. Using the energy skate park basics, let's observe the transformation of kinetic energy and potential energy of the skater as she skates along the curved track. When thus her potential energy become high, how about her kinetic energy? When she is on the end of the track, left end or right end, her potential energy is maximum since her height from the ground is highest, which is 6 meters, while her kinetic energy becomes zero since her velocity at that point becomes zero. Energy consistently changes forms. With the transformation of potential energy to kinetic energy and vice versa in the previous examples, we have seen that energy is conserved. This is in accordance with the law of conservation of mechanical energy that states energy cannot be created or destroyed, only transformed.